Hey guys, we're nearly done with Unit 7, that is Inference for quantitative data, and today we're looking at our last lesson, that is Inference for two population means. So we're going to be making confidence intervals and conducting hypothesis tests. So our EQ is going to reflect that. What is the point estimate and test statistic for inference for two population means? So I'm going to run through these lecture notes really very quickly because I'm posting it for you guys to be able to read. It's dense, it's got lots of notation, but most of it's familiar. In fact, I pretty much just copy and pasted everything from this. I got it from the 10.1 notes, Inference for categorical data with proportions, because it's extremely similar. It's all the same stuff we've been doing. It's not hard, it's just more easy. All right, so let's get through this as quickly as possible. You'll see me jumping around. There's not too much annotation I'm gonna make here. Now, we often want to see the difference between two populations, and we can perform a significance test, or perform inference similar to what we did in Chapter 8 with confidence intervals, and in Chapter 9 with significance tests. Just like before, we start by looking at the sampling distribution, but this time we're looking at the difference between two means. We want to describe shape, center, and spread. So, shape. Remember, we want to see that normal-ish shape, where it's going to be the t distribution, okay? And that's going to be able to be used so long as the population is known to be normal, or the CLT is satisfied, or the difference in two sample distributions has no strong outliers, okay? So that's N1 must be greater than or equal to 30, and N2 must be greater than or equal to 30. Center, we know that the average difference between two sample means will be just the difference between the two means. So that's going to help us out. And then spread. This is where it gets a little bit tricky. This seems weird. How do we get this? Well, remember what sigma sub x bar is. Sigma sub x bar is sigma divided by the square root of n. But what we want is we want to consider one of them, sigma sub x1, and then we want to consider sigma sub x bar 2. So that's going to be sigma sub 1 over square root of n sub 1. And then sigma sub x bar sub 2 is going to be sigma 2 over the square root of your second sample size. Okay? Now, if we want to combine those two, whether we do plus or minus, it doesn't really matter. Well, then we are always going to be considering adding these two things. But remember, what we have to do with each one of these is we have to follow those rules of combining standard deviations, which is square them. So I'm going to do that for both of these. We square them, then we add them, and then we square root them. Okay? When we square root them, then we can see that sigma sub 1, that's squared, that turns into just sigma sub 1, and then we have n1, that's going to be, or the square root of n1, the square root and the square cancel each other out, so we're left with n1. So we have sigma sub 1 squared over n1, and then we have sigma sub 2 squared, and then the square root and the square, they cancel each other out, leaving us with n2, and the whole thing is still being taken the square root. So that's where we end up getting this formula. And we're only able to use that formula so long as the 10% condition is satisfied for both populations. Now, knowing how the sampling distribution behaves means then we can construct confidence intervals. Again, you want to always start by checking your conditions. You got your random sample or random assignment. You got your normal-ish condition, right? You're looking for the CLT to be satisfied. You might have to graph a couple of distributions of sample data, which, yeah, it stinks, but you got to do it. Or if you know your populations are known to be normal, then that's great. Sometimes with these, because they can be so labor intensive, you might even see the phrase, assume all conditions for inference are met, and hey, that's the gold standard. We love that because that means we could just go ahead and do our math. Finally, we do a 10% condition. Again, this can be written out in English. You don't have to use notation. That might make things a little bit easier. We'll try to practice that. And you can construct a confidence interval. So your confidence interval, you have to think about the point estimate. Remember, the point estimate is always just going to be the difference between two means. So my point estimate is going to be x bar 1 minus x bar 2. And then remember that we are working with means, so we're not going to be working with z star, we're going to be working with t star. And remember that we don't know what the sigma is, we don't know the population standard deviation, we're only working with sample information whenever we are working with inference. So you're going to see those. Or you could just use your calculator. You're going to be doing a 2 sample t interval, and then everything else should be pretty straightforward. The degrees of freedom is always going to be the smaller of the two n minus 1s. So remember that you have n sub 1
from your first sample, from your first population, and then you have an n sub 2, your second sample from your second population. So to find your degrees of freedom, you always have to find the both of those, okay? Lastly, you interpret it mostly the same way. You are blank % confident that the interval from blank to blank captures the true difference in means of the blank, the population, whatever it is in context, okay? You can also do hypothesis tests. The thing that's interesting about this is a lot of times I'm going to be using this notation for my alternate and null hypotheses rather than doing this one, which I've used before. So just kind of be on the lookout for that. Your test statistic is calculated the same way. I'm actually going to do this by hand a couple of times, so kind of recognize this and refer back to it when you print out your own copy of this. I will go through it with calculator, but hey, this actually really isn't that bad to do by hand. I want you to not be as intimidated by it. The only thing you have to remember here is that if you have a two-sided test, that's when you're using this guy here. If you're doing everything by hand, then you have to double your p-value, okay? Double your p-value before you end up making your rejection statement, okay? So, with all that being said, I know that was a whirlwind. You're just gonna refer back to this or try and walk through the steps with me as we go through this process. Let's take a look at examples. So here's our first example. We have a serum cholesterol level above 250 milligrams per deciliter of blood is a risk factor for cardiovascular disease in humans. At a medical center in St. Louis, a study to test the effectiveness of new cholesterol-lowering drug was conducted. 100 people with cholesterol levels between 250 milligrams and 300 milligrams were available for this study. 50 people were assigned at random to each of two treatment groups. One group received the standard cholesterol-lowering medication. The other received a new drug. So this is my big important part here, that I am comparing what happened with an old drug versus a new drug. And I've got two different populations, two different groups of people that are taking this medication. So this is not going to be a matched pairs test because we have two completely separate groups. It's not each individual receiving the same drug twice. It's two separate populations, two separate groups. So after taking the drug for 3 weeks, the 50 subjects who received the standard treatment had a mean decrease in cholesterol of 10 milligrams with a standard deviation of 8 milligrams per deciliter. And the 50 subjects who received the new drug had a mean decrease of 18 milligrams with standard deviation of 12. So right off the bat, again, this is like the 8th grade analysis. We can see, oh, well, the new drug had a greater mean reduction than the old drug did, 18 compared to 10, and we think that's good. Well, again, how do we know this is consistent? We have a lot of variability with this newer drug, so maybe there's a problem. So, does the new drug appear to be more effective? That's our question. More effective than the standard treatment in lowering the mean cholesterol levels. All right, so let's go ahead and jot down at least the given information and try and assign it some notation that's going to be helpful for us. So let's go ahead and call it ST for standard. So X bar of the standard was 10, and then we had a standard deviation of the standard was 8, and we had a sample of 50. Then we also had the new drug. I'll call that new. That was 18 with a standard deviation for the new drug of 12 and a sample size of 50 in that treatment group. Okay, so with both of these, we can see that we have the same size samples, and I can already start thinking about a couple of things that I'll have a degrees of freedom. That's going to be n minus 1, 50 minus 1 to give me 49. We'll keep that in mind. And then let's go ahead and say, let's let alpha equal 0.05, because I know I'm going to be conducting a test here. All right. So let's go ahead and try and figure out what would the null and alternate hypothesis be. Well, try to think about it logically. The null hypothesis, that statement of no difference, says that on average, they're the same. There's no difference between the standard drug and the new drug. So that means the mean of the standard drug is the same as the mean of the new drug as far as lowering cholesterol levels. Then our alternate hypothesis is that we think that the new drug is better. It is going to perform better at lowering the mean cholesterol level. So in this case, we would say that mu sub standard is doing a worse job, it is less than mu sub D. The reduction in the mean of the standard drug is less than the reduction for the new drug. That's what we're saying here. And this is where, again, it is a lot of times still critical for us to go ahead and write out our definitions for each of these. So I'll do that very quickly here, where mu sub ST and mu sub D are the mean reduction, I'll even call this true mean, levels in cholesterol for standard and new drug treatment groups. Okay, so we've defined our parameters, the two means, and we have our alternate hypothesis set up appropriately. We can check our conditions. This is pretty straightforward to do. I'll just change a color here just to make it a little bit more clear. We had random assignment, not random sampling, because this was an experiment. Random assignment. That's satisfied. We each have independent subjects. Every subject is independent with their cholesterol level of the next, so that can sometimes take the place of the 10% condition, but you could also think about, let's go ahead and assume that our population of people with these cholesterol levels is very, very high. And then you could say that 50 is going to be less than 10% of all people with this cholesterol level that took part in the experiment. So that's satisfied. And then finally, hey, this is good news. We have our CLT. That is indeed satisfied. 50 is greater than 30, satisfied for both treatment groups. So all of our conditions are met. All we need to do now is go through and make sure that we've got our alpha defined. We do. We've got a degrees of freedom. We've got all of our given information that we're going to need for our calculations here to calculate our test statistic. Let's go ahead and do that. So if I'm going to conduct a t-test, I need a t-score. And I know by looking at my formula sheet or my notes, that's going to be x bar sub standard minus the x bar sub D for the new, and then we subtract that from the mean difference, but that mean difference is going to be 0. Okay, and then we have our standard deviations. Our standard deviations were s sub 1 squared, so that was s sub st squared over this n st, and then we had our standard deviation of the new drug squared over n sub nu. And all of that's in the denominator. Now we have every bit of this. We have all of these pieces, so we can go ahead and write these out, where our t-score is going to be, very simply, 10 minus 18 minus 0. In the denominator, we have our first standard deviation, that was 8, all squared, and then I divide by 50, plus 12 was my second standard deviation that I had, divided by 50. And when I plug all of this into my calculator, give me a moment here, I'm going to end up with a t-score of negative 3.92. And you might be thinking, oh, that's a really low t-score, right? Well, the trick is with the t distribution, remember that's a little bit different than z-scores. So this might not be as all that crazy unusual as it seems. So we have to think about our t distribution is a little flatter than a normal distribution, but still it's the same idea, where we have 0 in the center, and then our t is going to be somewhere over here. That's negative 3.92. At least we're on the correct side of this, because remember that our alternate hypothesis said that we wanted to look at those that are less than. Okay, so here, this is what we are looking for. This is going to give us our p-value. And now we have to go to our trusty t-table. Looking at our trusty t-table, get the right document open here. Here we go. And we see, all right, well, what was my degrees of freedom? We said it was 49, but unfortunately 49 is not on here anywhere. The closest one we see is going to be 40. Remember, you always go to the lower of those two to find that degrees of freedom. And then we see, all right, well, my t-score was negative 3.92. We look at the absolute value of that, and we want to see, all right, well, where is that going to be located? It's going to be in between what two numbers? Here, I'm still not there, 3.307. I'm getting closer, 3.551. But still, it's going to be somewhere over here, which means let's go ahead and look and see where's that going to leave us up at the top here. So our p-value is going to be looking through here. It's 0.25 to 0.2, 0.15. All of our p-values are going down as we move to the right. So we are actually going to be somewhere to the right of this, which means we're going to be actually smaller than this number. So this is actually an extremely small p-value. Very, very unlikely to get this kind of sample if everything was just done by random chance alone, right? So now what we can do is we can write out our p-value that we know it's going to be less than this number here. We'll go ahead and do that. Open up my examples. We'll go back to these guys. And we say that our p-value, based off of that t-table and the degrees of freedom, I need to adjust that I was looking at degrees of freedom of 40, is going to be less than 0.0005. And that is definitely less than alpha. So if our p-value is less than alpha, what does that mean? We should reject the null hypothesis. So how do we write out this rejection statement, right? This is where it can get a little bit tricky. Here was our question. Does the new drug appear to be more effective than the standard treatment in lowering mean cholesterol levels? Yes. The new drug appears to be more effective than the standard treatment in lowering mean cholesterol levels. I have convincing evidence that the new drug is more effective than the standard treatment for lowering mean cholesterol levels. In patients like this. This is also an extremely important part when we are talking about an experiment. Our scope of inference does not include saying something about two different populations. Because two populations is the only way we can make inference about populations is if we have random sampling. We didn't have random sampling here, right? We had a random assignment of individuals into treatment groups. So we have to make that statement here, okay? Now, if we want to do this in the calculator, we absolutely can do that. Let's open up a calculator page, and we go into our menu, and we want to go into, remember, statistics, and then we want to conduct a stat test, so we choose number 7, okay? And then when we do number 7, we need to be a little bit careful here. Remember, we have two different samples from two different populations, so we do a 2-sample t-test. We are going to choose option number 4. Option number 4, we don't have all of the data. All we have are the different statistics. So from this drop-down menu, we choose stats, and then we go ahead and hit OK. And there's going to be a lot of information to punch in, but you have all this information here. Your first group was 10. Oops. And then our next group was that was 8. Sample size for the first one was 50. X2, pretty easy. That one's 18. This is where we write down all the information that we need. Excuse me while I fix a couple of things here. 18, 12, and 50. And then our alternate hypothesis, we need to change that. Remember, that was not our alternate hypothesis. Our alternate hypothesis was using a less than symbol. So we use that same less than symbol here, and then we hit OK. We should end up with the same exact results. Let's check it out. T-score, negative 3.92232. This uses a more precise calculation for degrees of freedom. It's way beyond the scope of our course, but you can go ahead and record this if you were going to say two-sample t-test, and then look at your p-value. Extremely small, 0.000088, which means it is virtually impossible to get a sample like this if we assume that the null hypothesis is true. So it's virtually impossible to see a sample where we got this much more reduction in mean cholesterol by taking the new drug if there's absolutely no difference between the new drug and the old drug. Okay, so if I were to write out my results here, if I wanted to do that, I would say that I'm conducting a two-sample t-test. I would want to write down my t-score of negative 3.92, my p-value of 0.00008, 9, and then we had degrees of freedom was something around, I don't remember, you guys will probably yell at me for getting this wrong, but 85. Okay, same idea, right? Super small p-value, stupid small, leads us to that same information. Let's go and take a look at one more example, but this time we'll make a confidence interval. Okay, last example for the day. Here we've got 2000, question number 4. Baby walkers are seats hanging from frames that allow babies to sit upright with their legs dangling and feet touching the floor. Walkers have wheels on their legs that allow the infant to propel the walker around the house, long before he or she can actually even crawl. Typically, babies use walkers between the ages of 4 months and 11 months. Because most walkers have tray tables in front of the block, babies use their feet. Child psychologists have begun to question whether the walkers affect infants' cognitive development. One study compared mental skills of a random sample, not an experiment, this is a random selection. So we have a random sample of those who used walkers with a random sample of those who never used walkers. So we got two groups, walkers and no walkers. Mental skills scores averaged 113 for 54 babies. So again, that's showing me an X bar. And these were the ones for walkers. And then we had a standard deviation of 12. And then 123 for babies who did not use walkers with a standard deviation of 15. Is there evidence that the mean mental skill score of babies who use walkers is different from the mean mental skill of babies who do not? So, again, what we're doing here, we're looking for a difference between the two. Okay, so I can immediately start thinking about this. Let's go ahead and say if we're looking at the difference for mean scores, then I would say the mean of the group that uses walkers would be no different than the mean for no walkers. Okay, that would be my null hypothesis. My alternate, though, is not that one is better than the other. My alternate is simply that they are different. So my mean of walkers is not equal to the mean mental skill score of no walker group babies. Okay? So we think, all right, that means I'm going to be doing a hypothesis test, right? No, we can actually do a confidence interval for this. Let's jot down some of the given information. I'm going to clean up some of my circling and such here, just so I can get a better picture of the numbers. And let's see, I have my walker group. I will call that X bar for walkers is going to be equal to 113. And we had a standard deviation for walkers of 12. And we had a sample for walkers of 54. Now, in the non-walker group, I'll call that X bar NW, we had 123. So it looks like the no-walker group has a higher mental skill score, right? It's 123 compared to 113. Well, that's a little bit too rudimentary. We want to do something that's a little bit more fancy than that. So we also take into account the variability, right? And we want to see what do all of these different samples really tend to look like. So here we had a score of 15. Now, we also had a sample that was a little bit bigger, not by much, it was just one extra kiddo, right? 55 in this group. Now, we can go ahead and say that we can have a degrees of freedom here of 54. We take our smallest of the two samples and then we subtract 1 from it, giving us 53. You might remember from the previous example that we don't have a degrees of freedom of 53, so I'm going to go to the next tens group that's lower. And now I want to make a confidence level here. So I'm going to make a confidence level equal to 95%. Okay? So if I look at a confidence level of 95%, then let's see, we know we need a T star. And T star is actually just going to be provided from us from our trusty t-table. That's why we like it. Okay, so if I go to my t-table, clean up my writing that I had from this previous one, I look at the row that has the corresponding degrees of freedom, 50, and then I look at the column that's going to have the confidence level that I want, right? So 95%, and then I'm going to look and see what is the intersection between those two, and it's 2.009. So there's my T star. So let's go ahead and jot that guy down. T star for this confidence interval is going to be 2.009. So I've got all my given information. Now let's go ahead and check our conditions. Conditions are going to be easier for you to check than you might think. We have a random sample. We had actually two random samples of babies. So that's satisfied. Boom, done. CLT, we know that's satisfied because 54 and 55 are both greater than 30, so CLT is met. And then our 10% condition, well, we know that our smallest sample, or our largest sample, we can say 54 and 55 are both going to be less than 10% of all babies, right? So, super simple, right? Whether they use walkers or not, we know that's going to be less than 10% of all babies that do or do not use walkers. So, easy enough to do. Let's go ahead and make sure we define what our means are over here, where mu W and mu NW are the mean mental skill scores for babies that use and don't use walkers, respectively. Okay, so easy enough, not too much work. Now let's go ahead and actually make our confidence interval. So when we make our confidence interval, what we want to remember is just kind of the general format, that our confidence interval is going to be the difference between two different groups. So we have x bar 1 minus x bar 2, and then we plus or minus it with our margin of error. Our margin of error is found by that critical value, which was the t star, times the standard error. So that's the standard deviation for the difference between the two, and that's our s1 squared divided by n plus s2 squared divided by n, and we take the square root of all of that. We've got all of this information here. This is just plug and chug and then let the calculator do the rest. So my confidence interval, x bar 1, that's my x bar group with walkers. That's 113. And then my group without walkers, that's going to be 123. My t star, we found that already, 2.009. Square root, the standard deviation of the first group, that was the walker group, that was 12 squared divided by the sample size of 54. My second group had a standard deviation of 15 divided by 55. Go to your calculator, punch all this in. It's not too tough to do. You're going to have to do it in 2 steps, but you should get a lower bound of negative 15.2225 and then a upper bound of negative 4.7775. You might think, wait, that's weird. Why do I have an entirely negative confidence interval? Well, remember, what is it that we are trying to say here? That there is a difference between these two groups. And what did we do? We did a difference between these two means, a difference between these two populations. The other way that we could write out this alternate hypothesis that would actually make it a little bit easier for us to understand would be that the mean mental skill score of the walker group minus the mean mental skill score of the non-walker group does not equal 0. Now, think about that alternate hypothesis as we look at our confidence interval. Our alternate hypothesis is that there is a difference between these two groups, that it does not equal 0. Well, is 0 a plausible value for the true difference in the mean mental skill scores? No, because 0 is not captured in the interval. Since 0 is not captured in the confidence interval, it's not plausible that there is no difference between the two, so I reject the null hypothesis. I have convincing evidence that there is a difference in mean mental skill scores between Walker and no Walker babies. There it is. You've just used a confidence interval to essentially conduct a hypothesis test. Not only that, it gives us more information, because what does it tell us? The fact that this score is entirely negative, which mental skill score is bigger? Well, if it's negative, it must be that second number. And which one was our second number? It was the no Walker group. So it appears that not having the Walker actually does seem to be correlated in some way with an increase in mental skill scores. But the question here is, does it cause a change, right? Take a look at part B. Suppose that this study, or a study using this design, found a statistically significant result, which we did. We found a statistically significant result. We rejected the null hypothesis. Would it be reasonable to conclude that using a Walker causes a change in mean mental skill score? You say, yeah, look, it's different, right? It's lower. The answer is actually no. Remember, we have to think about our scope of inference. Was there any random assignment of treatments? No. No random assignment of babies to use or not use a Walker. And if there is no random assignment of treatments, that means this is not an experiment. And if we don't have an experiment, if we don't have that random assignment of treatment, we can't make a cause and effect conclusion. And that is that. Thank you guys very much for watching. Have a wonderful day.